Now let us go to our next session, that is the study of overcurrent relay. What we'll do here, we'll construct a simple power system, then we'll connect a relay along with a CT in the line, and intentionally we'll create fault. And here we'll take only single phase system. Now you can see this is the power system we have chosen. A source, the main parts of the source, 400 RMS, 10 kilometer transmission line with these parameters: resistance per kilometer, inductance per kilometer, capacitance per kilometer. And we have taken pi section model, and we have taken just a single section, and it is directly connected with the load. The rating of the load is 400 volt, 50 hertz, 4000 watt, and 200 var inductive, and 1.001 ohm small resistance is connected in between source and the transmission line. And question may come why it is connected. It is just connected because if it is not connected, then the signaling, MATLAB signaling will give some error. Okay, so to avoid that error, we are just connecting this. No other reason. The MATLAB signaling doesn't allow us to connect this source directly with the transmission line. So that's why one small resistance is connected in series with that. So we can easily construct this circuit in MATLAB Simulink. All the components are available in the Simulink library. And next, for this circuit, we can easily find out the RMS current which is going to the line. How? We have to connect a current measurement block here, and we can connect a CRO, and also power GUI block should be connected to get the steady state value of the different quantities. And another way to get the RMS value is we can also connect a RMS calculating block available in the library, which is known as the continuous RMS, and it is directly connected with the display. So all are available in the library, so you can get this RMS value directly. So this is the diagram. So this is the power system. I have now drawn this again, given the dotted. Now one current element should be connected here, current measuring block, and it is connected with the continuous RMS block. And it is directly fed to the display to get the RMS value of the current. Or what we can do, we can directly connect this with a CRO, and we can go to the power GUI block. Then there we can find the steady state value of all quantities. So there also we can get the big value of current, the RMS value of the current. The angle also we get. The angle cannot be obtained from this display. But in Power BI block, we can get the value as well as the angle. That is, the complex quantity can be obtained. So in your experiment, first of all, you have to get this steady normal current which will be flowing to the circuit. Run it and note the RMS value of the current flowing in the circuit from the display or power block. Now, the relay cannot be directly connected with the line, so the CT is chosen. N is to 1. 10 ampere current is playing in the primary, 1 ampere current will be playing in the secondary. So how this can be designed in Simulink? There may be CT block in the library. Here we have used different logic. The current is being taken and a gain of 10 by 1, that is 1 by 10. The gain value is 1 by 10 is used, then continuous RMS. So this is the secondary of the CT, you can say. It's very simple, the logic. Current is taken, it is divided by 10, then take RMS value, then it is connected with the display. So you can get directly the RMS value of the CT secondary. Okay. Then the overcurrent relay, how it is designed, how logically it is designed. So we have seen the PSM should be calculated first. So to get the PSM, that current should be sent to this value, and that should be divided by the set value of the current, which may be 0.5, 0.5, 0.75, 1, 1.25, 1.5, 1.75 to any of these 7, as I've said in earlier. So that divided by that, so you have to take this block, division block, and ultimately the output will be your clock setting multiplier. And also you can connect a display block to get the value of the display without calculating. We can directly get from the display. So the display, one display block may be connected directly at this point to get the clock setting multiplier. Then obviously one conditional block should be added, conditional switch, uh, which is operated in this logic. So if it is seen that the secondary current is greater than the set value, it will operate. Means the condition is that if the clock setting multiplier, if it is greater than 1, here you can set the value 1. If it is greater than 1, then it will operate. Means this clock setting multiplier will come to this point. And if it is less, not that, if it is less than 1, then the value will be 0. That means if it is 0, then the time taken will be very, very high, means that this will not rotate or the relay will not operate. So it will operate only when this ratio, this clock setting multiplier is greater than. So when it is greater than 1, we can directly get the clock setting multiplier, this value here. Then we have to put another block here just to determine the value of the operating time. Now for that, we don't have any relay here, no hardware relay is there, so that we can directly get it. So logically, how can it be obtained? So we know, or the specification of this relay will be given by the manufacturer. In any relay, electromagnetic relay, you can see uh, there will be operating time versus clock setting multiplier given on the body of the relay, and this value is like that. And as I've said, it is it will be like that. Okay, and you can see the definite minimum time means when the clock setting multiplier is 20 or more than 20, the time taken by the delay will be same, constant. So you get, it is obvious from this data also that when the clock setting multiplier is 20, then it is 2.2 second. Then 22, then also 2.2 second. Then 24, 2.2 second. 26, then also 2.2 second. So this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. This 18 data should be given to a block, which is known as the lookup table. So you have, I think, the idea of lookup table, that is nothing but XY plot. So if so, this is a lookup table. So in this table, you can get it in Simulink library. You just drag it to the file and click on this, and you have to put all these values there. PSM versus operating time. So these all data should be given there. So accordingly, the block will set a card. The block will set a clock. So then, as per your PSM, it will provide the y-axis value, that is operating time, and that is only for 100%. Now time setting may be different from 100%. So that's why this is not enough. We have to multiply this time setting with the output of this lookup table. So the output from the lookup table is the operating time when the time is set at 100%. So here you have to put the value of the time setting, so that ultimately what will be the operating time that can be displayed in this display block. So that is what you have to do in your lab. And another important thing is the fault. Intentionally, we have to put a fault block. So there is a fault block in Simulink library. You get it, and the timing of the fault can be set so that you can initiate the fault as per your choice, say 0.1 second or 0.001 second. Okay, so the fault can be set. And another block is the switch block. If it is seen that the relay, uh, the PSM is more than 1, it will operate, and after this operating time, the circuit breaker will be automatically open. Okay. Now, in laboratory, what you have to do, first of all, you have to set this PS1 and TS1 and vary the fault resistance. That is, if you vary the fault resistance, the fault current will vary. So to vary, to get the different fault currents, we have to vary the fault resistance from the small value to some high value. So 0.01, start from 0.01, then 0.1, then 1, 5, 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. So for all of these fault currents, you have to fill up this table. The primary current, the secondary current, the plug setting multiplier, which you can calculate by yourself or can be obtained from the display block, and the operating time that is also obtained from the display block. So for PS1 and PS1, you will get result table. Then do the same thing for PS1, PS.5, then PS.5, PS1, then PS.5, PS.5. So you get four set of data. So you have to plot all these four set of data in a single graph paper. Okay, and ultimately the Simulink file will look like this. So here's the power wave block. This is the source. This 0.001 ohm resistance current block, current measuring block. Then pi section line 10 kilometer. The parameters are given here. Then it is connected with the load, inductive load, 4000 watt and 200 watt RL load. Okay. Then this is connected with the gain 1 by 10. Then continuous RMS block to get the secondary current. And then the current is directly divided by the set value of the current to get the PSM. It is obtained in this display block. Then this PSM is sent to this switch. The switch will see whether the PSM is more than 1 or less than 1. If it is seen that more than 1, this switch position will be like that. So it will take the PSM value, and from this lookup table, it gets the time, operating time for 100% setting. So setting may be more, other than 100%. So that's why this setting should be multiplied with the operating time to get the actual operating time. So this is the actual operating time. And if the PSM is not greater than 1, less than 1, then it will take the value of 0. So for 0 PSM, the time taken will be very, very high. It may be say 70, 80 or more. So in that case, if the value appears to be 70, 76, 80 like that for 100% time setting, so you just avoid it. You can assume that the relay is not operating. Okay. So that's all.